Yes.
Hello, am I audible?
Yes, you are. Are we?
Okay. Yes, you are. Okay. Do I start with my presentation
No,
then?
just wait for 5 minutes. We
Yeah,
will let
sure.
you know.
Yeah.
Thank you. Good morning, respected judges and all present here. We would like to extend a warm welcome to all of you. As we all know, Encore is an intercollegiate technical paper presentation contest organized by the IT department of Don Bosco Institute of Technology. We have been successfully organizing Encore for the past 4 years and have been receiving an overwhelming response. In 2015, Encore was conducted as the first ever online paper presentation contest in Mumbai University and has been virtualized ever since. The purpose of this competition is to encourage undergraduate students to write and present technical papers based on their project. It also gives them a chance to interact with the industry and obtain reviews on their project.
I would now like to introduce our judges for the Comms and IT paper. Our first judge for today is Mr. Suhas Nayak from TCS. He has more than 15 years of experience in the IT industry. He is currently working as a project manager for a critical initiative for TCS top management. He has also previously worked in various roles as technical lead, delivery manager, business analyst, sales lead for various assignments of TCS both in India and abroad. He has also handled teams of size 50 plus and has worked for various TCS clients. I would now request our HOD, Mr. Shiv Negi sir, to hand over a bouquet as our token of appreciation.
Moving on to our second judge, we have Dr. Amay Kumar Tripathi. He has completed his PhD from IIT Mumbai and he has published many national and international papers in reputed journals. He has more than 15 years of teaching experience. He is currently working as the Dean R&D at DBIT and also handles the consultancy assignments for outside companies. I would now like to request Professor Tayyab Ali to hand over a bouquet as a token of appreciation.
We may now begin the competition. Our first paper for today is from Comms, that is with paper ID CE013, titled Automatic Parallelization of C Programs for Cluster and GPU Computing. The authors are Aisha Parveen, Nida Prathankar, Harshala Boir, and Amroz Siddiqui.
May I start over with the presentation?
Yes, you can start. Please.
Okay. Thank you. Is the presentation visible?
Yes,
Okay,
you can
thank you,
start
sir.
now.
Okay. Good morning, everyone who is watching the presentation right now. This is Aisha, and I am from Father Agnell's Engineering College, Vashi, and I am from the computer department. The project is automatic parallelization of C programs for cluster and GPU computing. So, starting over, this is the outline that I'll be presenting today. The project is basically divided into two parts as specified in the title, that is for cluster computing and the GPU computing domain. We have developed two tools called as the C2 MPI Translator and the C2 CUDA Translators. Let's start over with the C2 MPI Translator. The C2 MPI Translator is a tool that automatically converts the C programs to parallel programs that can run on a distributed architecture, that is on a cluster of computers connected together. And the second tool that we had developed we had called it as the C2 CUDA Translator, and it takes in as C program as input and it automatically generates files for the CUDA program that can run on a GPU-enabled computer. Now, for developing any application, there should be some need to it, of course. So what is the need for automatic parallelization? Like, consider the research centers like DARC, where a lot of research is carried out in the field of parallel computing. Huge amount of code is parallelized every day, and a lot of programming effort is taken from the side of a programmer, since it's a very difficult task to parallelize codes. So there is definitely a need for developing some tools that can automatically do this process of parallelization of codes. Now, starting over with C2 MPI Translator, it is designed for the distributed architecture, which is shown here, which is a master-slave architecture. In our case, we had connected 4 processors together, 4 standalone computers together using a KVM switch, such that these processors can communicate with each other. So what the master does is, the master divides a big task into subtasks and divides it and distributes it amongst the slaves. Now, slaves compute those intermediate results and give the results back to the master. And the master combines all the results back to produce the final results. Now, as we can see that there should be some, since we have connected all the processors together, there should be some mechanism that could deal with the communication process amongst these processors. So we have used the Open MPI, that is the open source message passing interface, using which all these processors communicate with each other. Like the OpenMPI library provides functions, the predefined functions for communication using messages like the MPI send or MPI receive messages. Now, since it is seen that yes, there are a few hurdles to parallel computing as well. A very big hurdle is the communication time. Since we can see that these processes need to communicate with each other, so it's not just the running time on each process, but the communication time is also involved. So a programmer's job is to decrease the communication time to the maximum, as much as it could be possible. Now, the second hurdle is that there are sections in a program that inherently cannot be parallelized. So a programmer definitely cannot touch on these sections, but the programmer can work on the communication time. And it is seen that in traditional systems, a lot of redundant data is transferred between the nodes. Like, for example, if there's an array between A of 0 to A of, say, A of 8, and I have 9 elements here, and I want all my slaves. Consider I have 3 slaves for computing, and every slave is dealing with just 3 elements each. But in traditional systems, the entire array used to be transferred. So genuinely, there's a lot of redundant data that is transferred on all the nodes. So the best case would be that to reduce all the redundant data by transferring only that data or only that code that is required by that particular node for processing. Now, there is a solution to it called as a Polyhedron Model, which is basically a mathematical framework where every iteration in the loop is represented using lattice points. And the Polyhedron Model successfully calculates the exact amount of data or code that is to be transferred amongst the nodes. And since each iteration is represented in the form of points, each iteration can be seen clearly. So there is a very fine-grained analysis that can be performed to that particular code using this polyhedral model. Now, not only just the representation, but dependencies also need to be dealt upon. Like there will be dependencies. Like, for example, if any piece of code, like the second line needs the results from the first line. So there are dependencies. So, and this is an example that I have shown to explain how dependencies are resolved using the polyhedral model. Since I have two loops here containing I and j, it's a plane. Why it's a plane is because I is represented along the x-axis and j along the y-axis. And all these nodes represent all the iterations S1 and S2. The S1 and S2 are two sections. S1 is represented using the black dots and S2 is represented using the blue dots. And all this code is automatically converted and chunked down into pieces such that these are independent pieces that can be transferred to all the nodes. And all this work is done using the polyhedral representation. Now, the testing of C2 MPI Translator. Okay, this is the tool where you just have to need to give the C code as input and you get the parallel code ready as the output within a few seconds of time. Now I'll be showing the serial and parallel execution, a few screenshots of that. I have executed here the matrix multiplication program using GCC, that is normal serial execution, and the time taken is 20 point something seconds. Now, using the tool, I have executed the parallel code here. That is the output of the tool I have executed here parallelly, and all these 4 time records are the time required in each node of the cluster. Now, as you can see, it from 20 point something seconds, it is so efficient that it is only point something seconds here. So, as we can see, it is highly time efficient, and yes, it is very highly time efficient. And I've tested on 2 benchmark programs with varying values of n and showing serial and parallel execution running times in milliseconds. As you can see, there's a lot of efficiency that we can see as compared to normal serial execution. And you can see that this is just the case when you have connected 4 processors together. What if there are 1,000 processors connected together? Imagine the amount of efficiency that can be achieved when thousands of processors are connected together, of processing elements are connected. But that is not practically possible to connect all thousands of standalone computers together using switches, etc. But yes, there is a solution to it. We can use the GPU computing. GPUs are small graphics cards that are present in our computers that have processing elements, that have thousands and 10,000s of processing elements which are used for processing images basically. And the same concept can be done to parallelize the codes as well. But again, the same old story is that normal C programs cannot be executed on a GPU. That is a graphical processing unit. And also that manually parallelizing is also very difficult. That is converting a C program to a CUDA program. It's also very difficult. So the tool again, we have called this tool as the C2 CUDA Translator, where you just have to give the C code as input and you get the CUDA codes ready. .cu represents the CUDA extension. And these codes can run on a GPU successfully. Okay, this is how a CUDA architecture looks like, where CPU and the GPU communicate with each other. First, all the variables that are there on the CPU are copied onto the device. That is, the memory allocation is done in the device. And then all the computations are performed on the GPU here, on the device memory. And then finally, the results are copied back to the host, such that the user can have a look at what the results are. And also that the final results obtained are copied, followed by freeing the memory in the GPU such that the GPU device memory is not wasted. Now, this is how the GPU programming works like. In the device, this is the host, that is the CPU. This is the device, that is the GPU. In the device, there are grids generated, and each grid has blocks, and each block has threads. And the old example that I had taken, that is from A of 0 to A of 8, in the GPU architecture, every index is associated with thread. So in our case, there'll be 9 threads for every index. That is, A of 0 will be allocated with 1 thread, A of 1 will be allocated with 1 thread, and so on. So imagine the case where in the distributed architecture, we use 3 computers working together. And here we have, since it is a multi-threading architecture, we have all 9 processing elements that are working together. So the kind of efficiency that we obtain is very, very high. Now this is one block that I had shown which contains multiple threads. There can be multiple blocks as well, depending on the size of the input that you have. Now I'll be showing the testing part, that is the auto-generated CUDA files. I have my test cases in the test folder here, and I don't have the generated files here. Now let me generate the files here, passing it with the script or the parser, you can say. And I have tested on add.c, which is the program to add 2 matrices, and I've given a very high inputs such that the efficiency of this tool can be measured. And I have the 3 codes created here. As you can see, I have 3 files generated here: add_host.cu, add_kernel.cu, and add_kernel.hu, which was not present initially. Now, parallel execution on a GPU. And this CUDA programming can be done only if you have an NVIDIA-enabled GPU. And this concept was introduced in the year 2007 by NVIDIA itself. And this is how CUDA programs are executed using the NVCC compiler. I have passed 2 CUDA programs, and the output is written to the add executable, and the time generated can be seen here. Okay, so basically we have developed 2 tools for automatically parallelizing codes. One is the GPU and other is on a cluster architecture. Now the future scope could be and the current application to this, these tools could be that in the research centers, of course, like BRC, where there is a lot of code to be parallelized, a lot of human effort is wasted. Not only that the difficulty level is also very high. Hence, these tools can be used in research centers to decrease all those constraints. And these tools can also be taken forward by MATLAB or Mathematica, since MATLAB and Mathematica kind of domain-specific architectures require a lot of computing power, and hence, since we have done it with C programs, it can be taken forward to MATLAB and Mathematica as well. Okay, so it's like just give a normal C code as input. You don't have to learn parallel programming. You don't have to learn CUDA programming. You don't have to learn what MPI is, and just get over with the work within a few seconds, and your code files are ready. Thank you, everyone. I'm done with the presentation. Should I stop the screen share?
Yeah, I have some questions. So the first question to you is, how you are resolving those dependency that is in your polyhedral model that you resolve?
Yes, I'll show you the slide to explain that in a detailed manner. Okay, this is how a polyhedron model looks like. I have 2 iterations, I and j, I representing the x-axis and j along the y-axis. Now consider if I have k iteration, which can be represented along the z-axis. So I'll be having a cube. And if it is more than 3 iterations, like 4 or 5, I'll be having a hypercube. But in this example, I've used 2 iterations, hence I have a plane here. That is along the x and along the y-axis, which represents I and j iteration. Now, how it is shown is, like for example, take I is equal to 1 and j is equal to 0, then that represents this iteration. I is equal to 1 and j is equal to 0 here. So in this way, all the iterations can be represented using lattice points in a polyhedral model. Now I have taken up two examples of sample codes S1 and S2, where S1 is represented using the black dots and S2 is represented using the blue dots. Now, as you can see, in the polyhedral model, the overlapping dots you can see here, these represent the dependencies. When dots overlap, which means there's a dependency. Now the thing is, since the polyhedral model accurately calculates the amount of code that is to be transferred, it is all done using mathematics. It is found that by research, mathematical transformations can lead to the best transformations. So like in the rightmost section, if you see in the first for loop, that is j equal to 0, j is less than or equal to 7 and j plus plus. And here I is fixed as 1. So it represents the first vertical line shown in the polyhedral model. So in this way, the entire code is divided into pieces. But since there are dependencies here in this particular section, these two codes cannot be written on two different machines, of course. Like in this triangular section that you can see, you can't send S1 and S2 to do two different sections. Hence, they are serially computed on a single machine itself. All the other code is parallelized into areas like this is a line, this is a square, this is again a triangle, this is again a triangle. But this triangle has dependencies. So in this section, as you can see, the third section, that is S1 and S2 are written together since there are dependencies. S2 needs some data element that S1 is computing. So these two are written together and the rest of the code is written independently.
So if that number is increasing, for example, now you have taken 2 or maybe 3, but have you tried for such example like 10 such kind of things are coming, then what will happen?
10 such areas?
Yeah.
If there are 10 such areas, then there will be 10 independent loops that are written differently, and all of them can be sent to one processor each.
So this will be an automated process, or you have to be write a separate thing for this. I mean, auto iteration can be carried out.
Yes, the entire process is automated. Like you just have to give the C code as input, such that and we have concentrated mainly on parallelizing loops, since the for loops mainly, because a lot of computation time is spent inside loops. We have concentrated mainly on loops, and polyhedral model is basically for loops, the for loops. So,
okay, that's fine. Then another question that I have is that you have tested with the 3 computers, but if it is go beyond 3, have you anything testing you have done beyond 3?
No, in our college we had 4 commodity computers, so we had connected those. But yes, the scaling factor could be 10 as well.
All right.
But since that cannot be practically done, so we didn't try that out.
All right. And the application that you have talked about, that Mathematica, have you ever tried to do something for Mathematica?
No, we didn't try. I just searched that tools like Mathematica require a lot of computation power. So I think these kind of tools can be, the idea of these kind of tools can be used there also.
Okay, thank you.
Hi Aisha and team. I will quickly ask my questions. How much time did you took your entire team to develop these 2 tools?
It took us 1 year or more than 1 year. Yes, the project started in the end of
fine
6th
enough.
semester.
That's one thing.
Yes.
Okay. My question to you is, once you develop these tools, did you try to implement these tools in some application or project outside your college? Like you said, future applications, BRC and all, but have you at least tried to pilot your tools over there and bring some results, so that then we could have at least seen the results that way?
No, we didn't try that out.
Okay.
It was just recently done, and this tool has a lot of scope of improvement. Like since we are dealing only with loops, the future improvements could be that the entire domain of the C language could be parallelized. So after everything is dealt with, it becomes a fully fledged tool. Now for
Okay,
D
fine
level,
enough. So your plan is to give
that
this
could-
tool to the next batch who can probably pilot it to
Yes.
other organizations
yes.
and improve on the tool that way.
Yes.
Okay, fine
Yes.
enough. Yeah. Thanks, Aisha.
Okay. Thank you, sir.